Hello all, welcome to our video lecture. It's going to be all about currents and climate. You are going to first go to Earth and Environmental, your homepage. I wanted to point this out to you though before we get started with the lecture, that your newest notebook is right here. You can click it and print off a copy. I've already informed your parents that it's ready for you to either print out or pick up from the school if you need to. Please reach out to me if printing it off yourself or using it as a guide as you fill out your own notes is not going to work electronically. All right, and then our page that we're doing, which is still in our old notebook, looks like this. It's labeled Currents and Climate. So let's get started. You have one vocab word today, deposition. It's when sediments lose energy, drops or settle. Remember, we talked about how as the stream velocity changes in a river or even an ocean, the ability or the stream load, the amount of sediments that it can carry, changes too. So we see a direct relationship there. So as our stream velocity increases, our stream load or the amount of sediments will also increase. But if we decrease the velocity or quickness of the river, we are going to see a decrease in the sediments it's allowed to carry or able to, and then it's actually going to drop, right? So if you can't carry it anymore, it's going to drop those sediments that it once had. We see this when the water slows down. It could be like an obstruction, could be something like the river has widened, or it could be something like it's opening up into the mouth of the river, it's opening up into the ocean or the lake. We often see deposits right there. Even so, we can get things like deltas if it piles up over time, where the sediment actually has grown so large that it reaches the top of the water line. Okay, we have a couple more vocab words, so if you will just copy these down. Thermocline zone, which we talked about the other day, spring tides and neap tides, which we're going to talk about in another lecture, all about tides. And our bell ringer, we are actually not going to do because you don't know the answers to those yet. So I have just a brief poem for you. I think it's cool to start our lectures with kind of different ways, innovative, I would say. But here's a poetry reading about riptides. It is by, let's see, I can't read his name because my slide thing is in the way, but I did not write it. That's the moral of the story. Here we go. It's called Beware Dangerous Riptides, the sign warned. But there was the lovely Alice in her two-piece, charging out against the churning surf and good sense, and finally away from her gaggle of pals. Arriving way beyond where the rollers formed into pile drivers to create, I suppose, those riptides. But what did I care about? I would get to her alone beyond all the crashing and tell her something to make her laugh, always my only hope. And as the pull of the ocean carried me out way beyond where a swimmer like me had any right to be, and her strong crawl and athletic form brought her easily back to shore, I could have sworn I heard her laugh as she passed and say between strokes, "Careful out there, kiddo, no lifeguard today." Alice of my daunted dreams, I would die in the drink and never see her again. But she talked to me, though. For all I knew, she didn't know my name. So take from that poem what you will. It sounds like the author of the poem had a, not love affair, that's the wrong word, but a desire to meet this Alice who was able to swim out against the waves. She was a good swimmer, but he was not, and because of that, those riptides pulled him out. It's kind of interesting, and the reason why I bring up the poetry is because these natural phenomena that we're studying, like the stars, and right now we're studying the waves in the hydrosphere, they inspire people to not only think about them and go to them. Like the beach is a very popular place to go, not just for the sunshine, because it's beautiful and you can see all kinds of life, and it does it has the waves that you can either surf or boogie board on, or you can just enjoy the salt air, see the fish, right? But they just inspire people to be poetic or observe, even if you're not a poetic person or a very creative person, just observe the way that things go. We've been fascinated by these things, so it's really actually pretty cool that we're getting to study this. But enough of the more literal side of our study. We've already done that. So this is where our notes start. What is an ocean current? So our ocean currents are masses of water that flow from one place to another. And I know that sounds like a definition that really doesn't explain that much, but that's what it is, right? It's just a big body of water that flows from one place to another, and they can be on the surface of the ocean or in the deep water. And we're going to kind of discover how those two things are different, like why a surface current moves and why a deep water current moves, because it's not the same, and how they move. Ocean currents move more water and more. I read that wrong. Ocean currents move water and more. So here is some kind of accidental funny that showed us really how far these currents stretch. So number one, if you will, start on this graph with me. 29,000 ducks left China in 1992 and fell off the boat in the Pacific. 10,000 drift north. Of those 20,000, so you can see here. Here they go. They're off. They're on. The ship had broke. I can't remember exactly what happened, but the ship had broke down, and they fell. It wasn't on purpose, right? So these container ship, they dropped the ducks, and they went on their own little journey. So about 10,000 went north. The remaining went south and washed up in Australia, Indonesia, and South America. So you can see that the currents carried them from the coast of China and Japan here in the Pacific Ocean and pulled them all the way down to Australia and then even the coast of South America. So it spanned the South Pacific, which is pretty impressive to think about. And then here we go. Those 10,000s that drifted north, they took about 15 years, and 17,000 miles later, the Bath Toys are now on course for Britain's beaches. So it took them a long time, but they actually went around in between where the land bridge used to be in Alaska and Russia, and up over the United States and Canada and Greenland, and actually found their way into the Atlantic Ocean. So they've started in the Pacific, they went to the Arctic, and now they're in the Atlantic Ocean, and the current is going to whip them around all the way to Great Britain. So an accidental release of all these rubber duckies actually showed us, kind of gave us a better look into how the oceans actually move. So what are surface currents? These are the movement of water, and they flow horizontally into the upper parts of the ocean's surface. Remember, we talked about the surface zone, the thermocline zone, and the deep zone of the ocean. So in the surface zone, the currents are moving horizontally. So if you think like horizon, right, left to right, and this energy that drives the surface currents comes from the wind. So that's going to be a question that you will see, where or why do the surface currents move? It's because of the wind. So the wind pushes them across the equator, and they go with it's the easterlies and westerlies, those winds that are created from the Coriolis effect, which we're going to study in weather. But just know it's because of the wind and how the wind moves. That's how we get our surface currents. And the wind ultimately comes from the sun, but that's not something you'll learn about until later. Gyres are pretty awesome. I love studying them. I love studying the human impacts on our gyres, or somebody else called them something different. There's a couple different ways you can say this name, but they're large whirls of water within the ocean. We have 5 of them. So the North Pacific, South Pacific, North Atlantic, South Atlantic, and the Indian Ocean, and they're basically driven by a convection current in the water. So as the water moves from the equator, it gets warmer and warmer, and then is attracted up into those poles, and it's moved by the wind as well, but it's attracted to the poles, and then as it gets to the poles, it gets colder and it sinks back down towards the equator. And the same thing happens here. So if you think the equator's right here, so we warm up, and then we travel towards the poles, and then as we get more north up into up into the northern latitudes, it's actually going to cool down and start falling back to the equator again, and that happens here if we do the same thing in the southern hemisphere. So there are 5 of them. We're going to learn some pretty, I would say cool, but cool is not the right word, some pretty eye-opening things about these gyres when we study the human impacts on the hydrosphere. Why do currents move in a circular pattern? This is because of the Earth's rotation. So currents are deflected to the right in the northern hemisphere and to the left in the southern hemispheres from the Coriolis effect, if you see right here. So we're deflecting to the right and to the left in the southern hemisphere. So that is because of the Coriolis effect. The same thing happens when you get on a tilt-a-whirl. It's just kind of the way that things are moved. They don't necessarily go in a straight line. They are deflected a little bit, either to the right or to the left, depending on what hemisphere you're in. Ocean currents and climate. So oceans maintain the balance of the heat and energy, oceans maintain the balance of heat energy by ocean currents cycling between the equator and the pole region. So that same gyre effect that we see, it also, there's bigger ones. We call them the global conveyor belt, which we're going to look at in just a second. But it actually changes the climates that it is around. So it's one of the phenomenons, and it's why we see warmer or more stable temperatures in the coastal regions than we do in the inland regions because of this. I can't remember the word for it, but the effect that the specific heat of water has versus air. So when currents from low latitudes move to the higher latitudes, so think equator regions, they're going to bring with them that warm water, the warm heat, and transfer it to the cooler areas of Earth. And it warms up not only the water, but also the air, because water and air interact in a very similar, very tied together way, and they heat up similarly. So currents and climate, again, ocean currents are especially important to coastal regions. So warm or cool they warm or cool the air temperatures along these coastal regions. An example of this is the Gulf Stream, which warms the climate of Great Britain. So if you see, we start at the equator right here. The Gulf Stream starts, and with the warm water current, as it flows towards the poles, it's bringing its warmth with it, which warms the air and warms the climate. It's one reason that Britain is warmer than it should be climate-wise. So if you took away, pretended the oceans weren't there for a second, Britain would actually be a whole lot colder than it is. It's supposed to be a lot colder, but because of this Gulf Stream and because it's an island country, it benefits from the effect that I was talking about, that the warm water was warming up the air and warming up the climate. And the same can happen if you look at this cold current right here. As it comes down, it's going to actually make these regions much colder than they should be based on their latitude. Temperatures in North America, just in case you wondered. You can kind of see it right here, but if you can see, these coastal regions are operating at a little bit more of a warmer temperature than we do see inland right here. And still, it's pretty dominated by whether or not where the place is latitude wise. Like if we go right, I used to live right here, it's a lot colder right here, not only because it's inland and it's continental, it's a lot colder also because it's just more north than North Carolina right here. So it does have to do a little bit with how close you are to the water. Like you can really see it over here on the East Coast with California and Washington, and even down into here. And you can kind of see it with Florida and on the the East Coast. I hope I said West Coast, but not as much. And I think this is our last one for the day. No, we have much more. So this might have to be 2 lectures. Yeah, we're going to cut it off here. You're going to have 2 lectures for today, so hang tight. You will see another lecture in just a minute. Check your modules for it. Goodbye.